The second lecture on the theme of climate is given by Professor Hasselmann, who was also born in 1931 and spent his early years in the United Kingdom. After returning to Germany after the Second World War, he studied at the universities of Hamburg and Göttingen. His career progressed via appointments at renowned institutions in Europe and the United States, to the directorship of the Max Planck Institute for Meteorology in Hamburg, where he is now active. Professor Hasselmann's work has provided crucial insights into the relationship between weather and climate, and he has developed the fingerprinting methods that are presently used to assess the human impact on Earth's climate. And with this, I invite you to listen to Professor Hasselmann's Nobel lecture.
Honourable members of the Nobel Committee, ladies and gentlemen, my dear colleagues around the world, I am overwhelmed and still cannot believe the honour I received through the Nobel Prize. Receiving this prize is like giving a boy a box of chocolates simply because he was deeply involved in building a Lego structure. So thank you again for this honour, which I still cannot quite believe. I'm now 90 years old, and the research for which I am receiving the Nobel Prize was carried out over 40 years ago. Therefore, I have to thank Hans von Storch and my wife Susanne for helping to activate my memory again during the writing of this speech. Before I talk about my research on climate change, let me say a few words about my research before 1974, which led to my interest in climate change. I started by developing a basic equation for the energy balance in an ocean wave spectrum. This was a little different from the equations other colleagues had developed before. It was clear that one important term had been missing in the previous computation of the nonlinear energy transfer. I developed an equation including the transfer of energy from the peak of the wave spectrum towards lower and higher frequencies. This is described by a six-dimensional Boltzmann integral and was verified in an experiment JOHNSWAP, the Joint North Sea Wave Project, later in 1969 in the North Sea. Figure 1 shows the source terms of the energy balance equations with the input of the wind enhancing the peak of the spectrum, a low dissipation by wave breaking, and the non-energy transfer, S and L. The result is shown in Figure 2 as a set of directionally integrated frequency wave spectra as measured along an array perpendicular to the coastline. The peak is enhanced by the wind input and shifted to lower frequencies by the nonlinear wave interaction. I extended the nonlinear energy transfer technique also to other wave phenomena, such as seismic waves and also to plasma physics. When applied Feynman diagrams to the latter, the idea came to me that I could understand elementary particle interaction through a new theory by adding to the 4 space-time dimensions 8 extra dimensions, representing interacting nonlinear, non-gravitational wave components, as well as electromagnetic strong and weak forces. The theory combines the special and general relativity theories of Einstein. However, at the time I was already working on my first stochastic climate model. My ideas about particles remained a hobby. So, in the first and 1.5 decades of my scientific life, I studied mostly wave dynamics, wave interactions, and in particular ocean waves, and also air-sea interaction problems. This added substantial knowledge about the ocean to my thinking about physics and expanded my general interest, eventually leading to my investigations of weather and climate. But then something unexpected happened. In 1974, Raymond Luce, the president of the Max Planck Society, knocked on my door and did nothing else than offer me the opportunity to establish and direct a new Max Planck Institute, an institute to deal with the climate problem, in particular the perspective that the ongoing emissions of greenhouse gases would change the climate. When I was offered the directorship of the Max Planck Institute, I was happy that as a Max Planck director I would have complete freedom in research. For this I am very grateful. This was shortly after the Club of Rome had published its first warnings that mankind was destroying the planet. We had all read the book with great interest. My scientific curiosity was stimulated. My friend David Keeling had already started in 1960 to measure CO2 from Mauna Loa mountain on the island of Hawaii. At first, nobody took him seriously, but later his curve became the standard reference curve for model computations. Let me briefly explain the global balance in the climate system with two graphs. The radiation of the sun is partially reflected by the Earth, mostly by clouds. What remains heats the surface. This causes the surface to warm and will continue to do so were it not for the fact that the surface itself emits radiation in the infrared, and increasingly so with warming. Water vapor and some trace gases, notably CO2, are effective in absorbing energy radiated from Earth's surface before it escapes to space. While these greenhouse gases ultimately re-emit the energy they absorb, not all of it goes in the right direction. Some is emitted back towards the surface. This is what we call the greenhouse effect, and it forces Earth's surface to warm more than it would otherwise be required to balance heating from the sun. The effect is not small. Were it not for the greenhouse effect, Earth would be 30 degrees cooler, which would cause the oceans to freeze, leading to less absorbed sunlight and colder yet temperatures. So the greenhouse effect makes Earth habitable, but there can be too much of a good thing. Many processes, not just in the atmosphere, but also in the ocean and the biosphere, influence Earth's ability to balance its energy budget. Although I had been confronted by climate issues only in passing, I was convinced, as similarly also by Malus, that I would quickly learn what was needed, which I hope I did. When I began my climate research, everybody thought I would immediately buy a big computer. However, I first wanted to understand the basic theoretical principles of climate change. My first climate paper on the subject was the stochastic climate model, which provided an insight into the formation of long-term internal variations excited by short-term random weather fluctuations. It was shown that the short-term weather fluctuations can trigger long-term climate variations. For me, the first challenge was the question of what causes the variability of the climate system. Even if the data were far from being perfect in terms of accuracy, temporal, extension, and spatial coverage, it was clear that the spectrum of climate variations was mostly red. There are some spectral peaks, in particular the annual and diurnal cycle, tides, and also the ice age-related cycles. But apart from these, the spectrum was that of an Ornstein-Uhlenbeck process, which later went by the prosaic technical term of an autoregressive process of first order. The figure visualizes how we thought in the 1970s of the spread of the variance across timescales. Even though various modes had been found to be active in the atmosphere dynamics, such as the Southern Oscillation, the North Atlantic Oscillation, and many more oscillations, none of them were red oscillations, but instead processes associated with certain timescales. Indeed, the term timescale became the key for what followed. I saw an analogy with Brownian motion, where infinitely many small particles collide randomly with a heavy particle, which then begins to exhibit slow variations in response. My colleague Mujib Latif later formulated this in a nice picture. The short-term variability of the atmosphere can be regarded as tennis balls that are continuously thrown at a heavy medicine ball against the ocean. That at first does not respond, but begins to roll, or rather causes something to begin rolling, finally bringing about long-term climate change. Thus the ocean is, in effect, the long-term memory of climate. Thus I described weather and climate in terms of two timescales: short-term stochastic with stationary fluctuations, represented by a white spectrum, which is associated with the weather, and timescales of days and weeks and long-term variations of years up to millennia and more, representing climate variations. Some of the latter may be forced by external factors, greenhouse gases being a prominent example. But it turned out that eternal variability is also formed, generated by the short-term weather variability. The short-term variations are integrated by the inert climate system, resulting in a red spectrum, as predicted by an autoregressive process. For myself, as a theoretical physicist, this was pretty obvious, but in my academic surroundings, these ideas were a bit outlandish, even if some thinkers had dealt with such concepts before. I presented these ideas in my first paper as director of the new Max Planck Institute. It was published in 1976 as part one of a series on stochastic climate models in the journal Tennis. This paper is one of those which was apparently recognized by the Nobel Committee being worthy of this distinguished prize. As apparently not unusual with me, others thought my original paper was not an easy read, and I shall maybe apologise to youngsters who have trouble understanding the concept. But then a colleague asked me some 3 decades later if I would not like to write a clear update. I declined. By then, co-workers had developed the concept into a really simple form. In any case, the concept was soon widely accepted, and the door stood open for accepting the study of climate variations as an issue with a sarcastic but forced system. In the following years, co-workers of mine, among them Peter Lemke and Claude Frankeneuil, tested the concept I had sketched in part 1 of the paper, in parts 2 and 3, for a number of cases, for example of sea ice and sea surface temperature variations. The direct consequence of this stochasticity is the need to discriminate between climate variations due to external factors and those related to internal variability, for example, when the response of the climate system to elevated greenhouse gas concentration is considered. Unfortunately, we see nowadays a tendency to attribute all climate-related variations to external factors, disregarding the emergence of unprovoked internal stochastic excursions of the system. The internal variability is referred to in this context as noise. Thus, we look for the detection of so-called signals which cannot be explained by internal variability, and in case of success, compare this signal with the expected changes due to different forcings. If the similarity is sufficiently good, we attribute the signal to these external factors. This was the central subject of another paper of mine in 1979, published by the Royal Society in London. The first was to define the noise from the data, educate intuition or extended model simulations, and to construct expected responses or guesses of fingerprints to the possible forcing factors. To do so, the dimension of the noise space must be strongly reduced. Otherwise, the needed covariance matrix of the noise cannot be determined. One way to achieve this is to consider only that part of the phase space spanned by the dominant eigenvectors or empirical orthogonal functions, the EOFs. If the guess is sufficiently realistic, one may thereby determine a priori the subspace that is associated with the maximum signal-to-noise ratio. The patterns representing the subspace define then the optimal fingerprint. As before, after working out the concept, I began with co-workers to test and explore the merits of the ansatz. But we did not address the global warming challenge directly. Some 40 years ago, we had no good data sets describing the global variations of, say, sea surface temperature for a sufficiently long time. Also, the global climate model was still in a rudimentary state. The situation changed in the late 1980s. Several factors became more favorable, among them that a global warming became sustainable. Climate models had significantly matured, now with a dynamic ocean and sea ice components. Examples of possible greenhouse gas scenarios which were analyzed in the framework of the newly established IPCC process became available. Much improved datasets of surface temperature extending to the late 19th century had been constructed. Thus, we could construct powerful fingerprints, in particular in terms of temperature, as suggested by the models and the associated theory, of the effect of the disturbed atmospheric relative balance due to elevated atmospheric greenhouse gas concentrations. I had also invested time in updating the original publication from 1979 and was happy that my co-workers' assessment that it was a clearer description of the concept. All this ended in success, namely that my co-workers Gabi Hegel and Hans von Storch, together with myself, could reject the null hypothesis, according to which the observed warming could be explained by internal noise variations. Instead, we concluded that we had detected a signal emerging from the sea of noise. This is illustrated by a diagram from the 1990s, which shows in the artificial world of a scenario simulation the signal emerging from the noise in the observer data at the very end of the record in the 1990s, growing still more strongly in the simulation over a longer time. Furthermore, we demonstrated that most of the signal could be attributed to a combination of elevated greenhouse gas concentrations and of aerosols in the atmosphere. The diagram shows ellipses within which a 50-year trend would be consistent with different drivers. This was a significant result. In plain words, it was a proof that human activities are changing the climate, and that ongoing emissions will continue to change the climate until global emissions are massively reduced. We know now that ceasing global warming can be achieved only if emissions become zero or negative in the near future. This assertion becomes a cornerstone in the assessment of the IPCC and international agreements on how to respond to this perspective. On that occasion, the public and media interest in climate change increased, but I went on to other things. I returned to the issue, however, when global air temperatures rose to less than predicted for several years in the 2000s. This was a little startling, and I asked a co-worker to examine if this new observational evidence would contradict our claim of detection. They found that such a slow hiatus warming was quite rare but possible in global warming scenarios, and that we would have to reconsider our analysis of global warming if it continued. Fortunately, it did not, and our statistical proof of the reality of the human signal weathered this falsification attempt. As usual, failed attempts of falsification strengthened the original claim. After that episode, which was after my retirement, my interests wandered to different topics. One of them was the continuation of my efforts in the spirit of the economist Bill Nothaus to add a social-economic dimension to simplified climate models. The other was my attempt to unify particle theory with the concept of metrons, but so far my wife and I have not received a breakthrough in the physics community. But let us come back to the issue that is the focal point here. The concept of a stochastic climate system and the detection and attribution of climate change. While my two key papers dealt with specific issues, they were related to a more general concepts, which I published in 1998 under the name of Principal Interaction Patterns, or PIPs. In hindsight, these topics are connected, with PIPs being the general concept. For any analysis and prediction of variability, it is mandatory to reduce the number of degrees of freedom massively. This can be achieved only using a series of patterns or modes to expand the field of physical variables such as temperature or velocity. Thus, it makes sense to ask for patterns which are best suited for both analysis and for prediction. In the PIP concept, a small subspace is determined within which the dynamics of interest takes place. This is the signal space, spanned by vectors named PIPs. Using the PIPs, ideally, predictions are possible. The remaining infinite-dimensional space is ruled by stochastic processes, which are conditioned by the state of the signal space. The effect of these numerous stochastic processes on the signal space is summarized and described by parameterizations. To do so, one determines from observational evidence or detailed numerical simulations which effect is observed for a variety of states in the signal space. The distribution, or often the expected value of this distribution, is then considered the expected effect of the resolved components. In this way, a lower dimensional stochastically closed dynamics is determined, which is hoped will allow the analysis and prediction of the phenomena of interest. In its full generality and beauty, the PIP concept is still waiting for efficient implementation. So far, only a rather simple linear ansatz has been established successfully, namely the principal oscillation patterns, or POPs, which identifies real and complex eigenvectors representative of the dynamics with potential for prediction. The tropical, Madden, and Julian oscillation is a case where the POPs have demonstrated their potential. The detection and attribution part may be understood in terms of the POP concept, while the PIPs are the fingerprints of expected climate responses, which are embedded in a sea of internal variability. And we find the concept even in the design of climate models where a smaller part of the dynamics is resolved by the usual equations, while the signal space is limited to, for example, spherical harmonics of sufficiently large scale. The parameterizations describe the expected effects of the unresolved and thus unknown states of the smaller scales or variables not explicitly considered. Thus, in a sense, climate modeling makes sense only if such a separation into signal and noise is possible, even if the signals may represent very different animals. Let me say in addition something about climate computer models. Realizing that we needed extended computer facilities to develop climate models, I decided to set up a large computing center, the Deutsches Klimarechenzentrum, or DKZ, which was to be led by Wolfgang Zell. This move made it possible to carry out very large simulations with our new climate model. The computer system was updated regularly. The system continues to run smoothly in 2021. A further important task was to communicate the results of our research to the public. This really became a problem. I was not good in communicating with the public, and I thought I should rather use my time and talent concentrating on research. Two of my colleagues, Mujib Latif and Hartmut Kassel, took over this task most effectively. They became well known as a popular link between climate research and the press and the public, while at the same time contributing essentially to research. The public found the information interesting, but there was no adequate political reaction. People are not used to thinking in longer-term times. When former farmers passed on the farm to their sons, they took care of it in a different way than nowadays, where the current profit and the so-called high standard of living is considered more important. To inform and help the politicians, I developed coupled climate and economic models with my wife and later Dmitry Kovalevsky. I had always been interested in economics. Important aspects of the models, in my view, were the dynamical and multi-timescale nature of the system, both the natural sciences and the human parts. My view was that the inherent uncertainty of all model components calls for the development of models and statistical optimization models. Model results were important to guide climate-related policy making despite the inherent uncertainties of the models. It has now been 50 years since the Club of Rome published its first warnings about environmental changes by mankind, and we climate researchers have been warning for the last 40 years, proving scientifically that climate change is real. The IPCC combined all climate research results already in the support of 1990 and received the Nobel Peace Prize in 2007. However, not enough has happened to stop global warming. The next two graphs demonstrates how global warming has been increasing. The black curves show the variations of CO2 during hundreds of thousands of years. The blue lines show the difference in temperatures. And in detailed global distribution, you see the associated mean temperature rise between 1970 and 2020. First, the 50-year ensemble means, and then the 50 years ensemble standard deviation, and the 10-year ensemble mean, and the 10-year ensemble standard deviation. These scientific results should have spurred society and politicians to action long ago. A young girl of 15 had to place herself in front of the Swedish Parliament on the 20th of August in 2018 with a sign saying, "Skolstrejk för klimatet," in order to found a worldwide movement, Fridays for Future. Another way to stir up the public and voters more than we scientists have been able to. Thank you, Greta. I'm thankful to my family who had to leave with a husband, father, and grandfather whose mind was often far away in clouds, composed of noise, signals, waves, and spectra. And I'm thankful to the Max Planck Society which made this possible, and in particular, Raimar Rust. Lastly, I'm thankful to all my PhD students, postdocs, co-workers, colleagues, without whom it would have not been possible to explore the implications of my ideas. I ask for your understanding if I do not name all of these important people. I'm sure to have forgotten some. To solve the problem of global warming, it is now imperative to listen to scientists and engineers in order to understand the massive changes that are necessary to keep Earth alive and to address the climate, the collapse of the variety of species, the accumulation of trash, social differences, mass migration, starvation, population growth, etc., etc., etc. Our urgent advice to politicians: the longer we wait, the more expensive the necessary transformation will be. In addition, the cost of damage caused by extreme weather conditions, pandemic diseases, and global mass migration will only grow with time. We cannot wait. Thank you.